I start the recording here. I forgot to start in time. I just started to discuss the topics and what we will do in the near future, in the next 2 weeks. Okay. There was a definition also that directs some. Great. Properties of the orthogonal component subspace. That's also in the note. Orthogonal projection onto subspace, matrix projection onto a subspace, calculation of orthogonal projection, matrices of orthogonal projections, the best approximation theorem, vector notes. Okay, if I go back, this orthogonal projection and best approximation is here. I will tell you something from this, but not everything. This is too long. We don't have such time. Okay, there is this stuff that I will not mention at all. The decomposition of vector into components, optimal solution for system of equations, linear and polynomial regression, linearizable regression models, projection onto a subspace, projection on properties of projection, equivalent definition of the projection. When is a projection orthogonal? This is long, so this is I would need norms to explain you. Okay, now something that is useful. Okay, we had vector space. That's okay, and we also had basis previously. Basis just means linear independent vectors, and you could write all vectors as the linear combination of those vectors. Do you remember this? It's like coordinate systems. It's okay. If the basis vectors are perpendicular, that's useful. The extension, the general term generalization of perpendicularity is orthogonalization. Do you remember that you have two perpendicular vectors and you do the scalar product, then the result is 0. Do you remember this? We say that two vector is orthogonal if their scalar product is 0. In the normal life, in your science, in your work, in your studies, the two things means the same. But if you set to n-dimensional space or something bigger, then you can use the general definition. So what I wrote there, this blah 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 blah, it means you have basis vectors and the basis vectors scalar product is 0. So then they are orthogonal. And we are dealing with this system right now. If you have an orthogonal system and the length of the vectors is unit, 1 unit, I would say 1, okay, then it's an orthonormal system. You remember the definition of normal vectors. So there is something that we call orthonormal basis, OB, and orthogonal basis, OB, and there is orthonormal basis, ONB. Okay, let's go and continue this. Nope, I go back. Okay, let's continue. You can define the independence of orthogonal vectors. It is in the notes. I didn't explain you what is the best approximation, but for orthonormal basis, you also can do this. Doesn't matter, it is in the notes, that is in Hungarian. You don't speak Hungarian, doesn't matter. Which is important here? Orthogonal and semi-orthogonal matrix. A real square matrix is called orthogonal if its column vectors or row vectors form an orthonormal system. So you divide into parts the matrix. All columns are 1, 1 vector, and these vectors form an orthonormal system, or its row. If your matrix is not a square matrix, then you talk about semi-orthogonal matrix. If you have a matrix, the matrix Q size is n times n, and you do the transpose, then and multiply with the original matrix, and you got the original, not the eigen matrix, then that's a semi-orthogonal matrix. If you don't, yeah, just a moment. Top, where is it? This is an example for an orthogonal basis. If you do the multiplication, you always got 0. I mean the scalar multiplication. So okay, the orthonormal for example, could be many things, is many other. That's just a very well known example. If you do the multiplication, so these are about bases. What was the definition? If a matrix rows or columns are orthonormal, then the matrix is orthonormal. So for example, I do the opposite stuff. From this, this is an orthogonal matrix. Orthogonal matrix because if you divide this matrix to vectors, these columns, then you got that basis. That's an orthonormal basis.
Okay, but then I'm confused the difference between the orthogonal and the orthonormal basis because both of them the scalar product is 0 for both of them. So I don't know the difference.
The big difference is the following. The length of this is 2, 2, 3, 5. But normalization means the length is 0. So for this, for example, I can do the normalization. Then that's normal, because the length is normal. The original definition was sorry. So the normal vector of A is the vector divided by the length of the vector. So if I write, for example, so that was the normalization.
Okay.
And if I choose, so the length here is 1. Because if you calculate the length of this, it's 4, 13, 38, that's the length, and then you divide it. So the length is 1, and it direct somewhere, doesn't matter. It's okay?
Yeah.
Oh, that's why I don't want to teach you so many things. So this is at the end of this class. We will reach, we will reach my analysis studies. And then this is okay, sorry, I just forgot the original purpose of this. So, here is the example. You can see the first matrix, that's 1, 1, 0. It's so the first matrix, that's 1, 1, 0. So if you can do a lot of things, you can divide this into vectors using the columns, because the definition allows you to use 0 vectors, null vectors. But the best thing if you divide this into vectors from columns. So then you have no. Okay, it's better if I write this way. This is one vector, this is another vector. The scalar product is 0. But this is not a square matrix, so this is not an orthogonal matrix, this is a semi-orthogonal matrix. The next, B, well, you can use the columns. That will be interesting. Not for you, but for the Hungarians. So there are two vectors. And this is the same, so it's 0 again. So this is also an orthonormal basis. It should be an orthogonal matrix, but because this is not a square matrix, it's semi-orthogonal. And the last, oh, I like it. Okay, let's try this, this, and this. Okay, we are lucky. So this is an wait. For haha, okay. Okay. This is orthonormal matrix because these are perpendicular, not perpendicular, orthogonal, and I didn't check, but this is a normalization. So if you calculate, so this is 4, 9, so 13, 36. So altogether it's 49, and a square root is 7. So the length of all vectors is 1. Okay, it's great that we came here and didn't stay in the other room because I thought I won't need to write anything on the board. Okay, this says the following: if a matrix multiplied by its transponent is the result is 0, then the matrix is orthogonal or semi-orthogonal. Okay, so I can erase this. I also here this is my fate. It's here. So the statement says the following: if a matrix and its transponent, the matrix multiplication of a matrix, if a matrix transponent multiplied the matrix gives an eigen matrix, then it's orthonormal. Let's check this. Here, that's trivial. That's okay. But the transponent, sorry. You didn't tell me that sometimes I do write something and write something else. So that's why I'm not good in basketball, for example. I want to throw the ball and then something else happens. So here it's another out. Here. This is from there. And what is the transponent? Here it's the same. That's interesting. Actually, the transponent is the same. Yes. Okay, let's do the multiplication. 1, 0, 0. 0, 1, 0, 0, 0, 1. That's okay. Do you see? But here the transponent and the matrix are the same. Parallels there, that's a different stuff. 0, 1, 0, 0, 0, 1, 1, 0, 0. What is the transponent? 0, 0, 0. This comes here, this comes here. This comes here, this goes here, here, here. You can see, so I do the mirror on the window. Okay, so let's do the multiplication. This is 1. This is 0. This is 0. 0, 1, 0, 0, 0, and 1. So this is okay. This is also orthogonal matrix. Because So what we have done, the Q, actually I should have done in the opposite order, but so this is what we check here. But fortunately, I changed the order because this is a square matrix. It's not a problem. There, I have this A matrix, and let's start with okay, here is A matrix, 0, 1, 1, 1, 0, 0, 0, 1, and I need its transpose. This is 0, this is 0, this is 0, this is 1, this is 0, 0, and 0, 1. So this is the Q, and this is the transpose. I hope so. It's okay, it's okay, and it's okay. Okay, so I do the multiplication. Zero. Wait. Take, okay, I can do it actually. No. Wait, M. Okay, I think that here the opposite should be written. And then that's 1, that's 0, that's 0, and that's 1. And this is A2. So this is also an orthogonal matrix. Okay, here. B. I finish this and then. Okay, so the B. No, I wanted to write So using these trigonometric equations, I also got this. And we don't have time for CE. I will continue tomorrow. This one, let me see what we could do today, very quickly. So we went through the orthogonal matrices, and this is the, yeah. Oh my God. Okay, so we reached this orthogonal matrices.